Hi, good afternoon, everybody. I'm Günter Obiltschnig. Some of you may already know me from my open source work in C++. So my first question is, anyone here who've heard of the Poker C++ libraries already? Yeah, quite. The number is definitely growing. So yeah. Basically, what I've been doing for the last 10 years is, beside my work on Poker libraries, of course, I've been building lots of stuff based on the Poker libraries. So on one hand, I've built a couple of C++ frameworks that I'm also going to talk a bit later in this talk. I have built some cloud services for secure remote access for the Internet of Things, also with the Poker libraries. And my latest project that I'm going to talk about today is Machina.io, which is basically the Poker libraries taken as foundation and basically taken to a whole new level for IoT development with some special features that make it very easy for you to build software for so-called IoT gateways and IoT devices. For the German-speaking part of you, you might also be interested in the latest special issue of the X magazine on development for the Internet of Things. It also contains an article by me about how to build software for the IoT using C++. So the first question that I'm going to try to answer is, what is the Internet of Things? Anyone has an idea? Okay. So actually, was at an embedded software engineering conference for the last 3 days, and there are a couple of people actually asked the question, what does IoT mean? So despite the fact that the term IoT has been used in the media for software engineers for the last 3 years or so, still not that widespread. So let's see what IoT actually means. Basically, the Internet of Things is the network of physical objects or things embedded with electronic software, sensors, and connectivity to achieve greater value and service by exchanging data with other devices. And these things also have the property that they are uniquely identifiable. And actually, the term Internet of Things is quite old. It was formed in 1999 by Kevin Ashton. And actually, back then, Internet of Things was used for some kind of different applications. If some of you may remember, back then we had this RFID technology, which was soon to become part of every product. So the big vision was, when you go to a supermarket, you just put everything you buy into your trolley and go to the cashier, and then the cashier is actually just some kind of device that finds out what you have bought and then automatically charges your credit card. For various reasons, this vision hasn't yet come true. So the term Internet of Things is now being reused for something a bit different. So this is basically what the Internet of Things is all about. Of course, since in its name it's about things, which are connected smart products that combine processors, microprocessors, microcontrollers, sensors, and of course software with communications technology, of course. And then there is also the Internet in the name Internet of Things, which are the networks, which can be wired networks, wireless networks, like smaller sensor networks, like Bluetooth, Zigbee, but also larger scale networks, like 3G, 4G, and so on. And of course, we also need some destination where all this data gets sent to, and the whole computing infrastructure, the so-called cloud nowadays, where we hope to collect all this data that we get from the millions of sensors and make some sense of it. And actually, IoT isn't some kind of revolution, it's more of an evolution. So back then in the mid-90s, we had the web, where we started using web browsers, but the web browser was basically usually run on a PC, so you had to go to your PC to connect using an old modem to the internet, and then you could surf the web. Then in the middle of the 2Ks, we had mobile, with on one hand the mobile networks becoming more and more powerful, and of course with the introduction of the iPhone and Android devices. And this basically means that the internet became part of our personal life. So with the little device, you always have basically the internet with you. And then the IoT is basically the next step in that evolution, where the internet is not restricted to special devices, but basically becomes integrated in almost any device of daily use. There are some funny predictions regarding the number of connected devices that we will soon see around us. The predictions range everywhere from 20 billion to 50 billion. If we want to achieve this by 2020, we'll probably get things going and get up to speed. So I think these numbers are actually a bit very optimistic. The other question, of course, is why should we do the IoT? The ideas?
Because of the value we gain.
I mean, of course, as engineer, we'd like to say, yeah, because it lets us play with all this new, cool technology. But of course, there has to be some kind of business sense behind it. And of course, there has to be some benefit for the customer and also some benefit for the business, for the manufacturer that sells the device. And this is actually the big question right now in the whole IoT space. So basically, the technical problems are basically all solved. All the technical foundations that we need to build the IoT are basically there. In some cases, we probably need to wait until some technologies get even more cheap, but we need no special new inventions in order to achieve the IoT. And what the IoT has gives is basically two big opportunities for businesses. The first one is to transform existing business processes. Things like predictive maintenance, which means if there is some machine doing some work, we put a lot of sensors into the machine, and through the data collected by the sensors, try to find out early if something in the machine might go wrong, might break, might need servicing, or might need exchange of a part. Then, of course, better utilizations of machines, so it's easy to detect when machines go idle and do better planning to utilize them better, and of course, higher productivity. And there is also this nice concept of the digital twin that we'll see in the IoT, where basically, on the one hand, you have the physical device, the machine, the car, whatever, and on the other hand, in the cloud, in the data center, you have a complete virtual representation of the machine, including live data of every part of the machine to see how it works, how the environment is, and so on. And there, of course, are also a new business model, basically the anything as a service. So basically, the idea is instead of selling a machine at one point in time, getting some money for it, and then maybe have some service contract or whatever, the idea is not to sell the machine, but to sell the service of that the machine actually performs. So if the machine performs some kind of production step, then the customer pays 50 cents for every item that goes through the machine. And basically the manufacturer of the machine just provides through the machine that service. He takes care that the machine keeps running, that every consumables are refueled, that parts are updated, and so on. There are, of course, other business models. Probably have seen the Nest intelligent thermostat. And as you probably know, Nest got acquired by Google, and this makes for some interesting thoughts. So I think my Nest smoke alarm is going off. Google AdWords just pitched me a fire extinguisher and an offer for temporary housing. Yeah. But one of the essential ideas behind the Internet of Things is that things actually become software platforms. And a good example that we see is the Tesla. basically what Tesla did is they did not build a car. Basically, they built a smartphone, put some big batteries and wheels on it, and sell it as a mobility solution, say it that way. And what you see if you have a Tesla is there are software updates. And these software updates come over the internet, over the air. Each Tesla has a built-in mobile internet module. So it's basically online all the time. And every few months, you get a new software update that provides new features in your car. So the last software update actually provided the feature that the car can basically drive in certain situations, the car can drive alone. It's called autopilot. And if you look at YouTube, there are a couple of funny videos of people leaving the front seat and getting on the back seat and filming how the car is driving itself. And there are other videos where the car is driving on a curvy backside road, and suddenly it starts turning into the oncoming traffic. Which is not so funny. But the big difference is what Tesla is doing here. They're putting a technology that might not be that well developed already outside into the customers. And what they're gaining is they're getting an immense amount of data back from the cars, from the 50,000 cars they already have driving around everywhere. And they can use all this data to make the software even better. So how does a typical IoT architecture looks like? So on the first side, you have these sensors and devices. These are usually devices powered by smaller microcontrollers. You have 8-bit to little 32-bit microcontrollers. These things are usually programmed in C, some C++. And you have smaller network technologies like Zigbee. For example, in this case, this is a battery-powered Zigbee sensor, also Bluetooth and a couple of other technologies. And usually it doesn't make sense to connect every little device directly to the internet. The first hand, it's very hard to manage such a system. These things don't have user interfaces, so you cannot easily configure network addresses and things like that, so you need other technologies. And also there's a cost factor. You can put a Wi-Fi module or Ethernet into each of these devices that just cost a few euros or dollars. And therefore we have the concept of the IoT gateway, which is usually a Linux-capable device that on the one hand connects to these little devices, and on the other hand connects to the internet, and also can do some interesting things with the data it gets. And then, of course, you have the mobile clients that talk to the devices. You have web-based clients talking to the devices. And on the business side, you have so-called big data, where you try to make a sense of all the data. And if you look at the technology stack, you can see that actually what makes the Internet of Things interesting from a technology point of view is you have to deal with all the different layers, from the smallest embedded systems up to the big enterprise systems, and with all the different network technologies in between. And of course, there also is the very interesting question of how can we make everything secure. You've probably heard of that car that got hacked in the United States. There was a nice article that was published in the Wired magazine of some of the Wired writers writing it cheap, and a team of hackers gaining control of the Jeep while he was driving. So at first they got control of the car and switched the radio of the car radio and switched the car radio to a hip-hop station. Then maybe they turned on the wipers, and finally they disabled the brakes, and this was when it was too much for the driver, and to stop the car he turned into the ditch. And if you look at the different security advisories that are floating around the net, you can see that even things like Zigbee, which was, you might guess, designed by network professionals who know what they're doing, even Zigbee has very severe security issues. And to make matters worse, there are now even whole search engines devoted to finding actual things on the internet. So there is a showdown where you can, for example, search for webcams, search for industrial control devices, and so on. And yeah, if you go to that site and enter some search terms, there are some couple of interesting results that turn up. I mean, it gets worse when you find your own devices there, but at least you should know that these tools exist. So, and now let's get to some more interesting parts. While we're all here, we're here to talk about C++. So I'm going to talk a little bit about my newest open source project and how it was all built. So the interesting thing is about Machine.io, I have combined both the C++ word and also the JavaScript word. And I'm going to talk about some of the challenges that I had to solve in order to achieve this later on. But basically, this is the idea behind the newest project. So basically, you're going to write software for these kind of devices. And in order to write software for so-called IoT gateways, you have to talk to the different sensors. There are many, many different protocols and technologies that you can use to talk to them. And you're going to talk to cloud services. There are only two at the moment important technologies that you use here, HTTP and MQTT. And you can also integrate things like mobile clients and so on. And if we look at how everything is built, it's of course all based on the Boko libraries. And on top of that, we have added a couple of different frameworks. On one hand, what you want to do if you're building software for kind of an IoT gateway device is you want to be able to update the software even when the device is in the field. So the times where we're building software for an embedded device and the device gets shipped and then the software never gets updated again, except maybe for some very urgent security fixes. These times are over in the Internet of Things. So customers are basically expecting updates of the features of your device. As I said earlier, devices are becoming software platforms. And in order to build extensible software platforms, you need some flexibility. And this is the whole idea behind the so-called open service platform. It's basically a module system for C++. Module system less in the idea that's the new modules proposal for C++ 17, but modules in terms of deployment unit. So what you basically can do is you can take your C++ build shared libraries, put some metadata, put everything together in a zip file, add some HTML files, for example, some configuration files, and take the whole thing and download it to your device. If some of you are familiar a bit with the Java ecosystem, Java has a similar technology called OSGI. Usually I'm not a big fan of the Java world, but occasionally even the Java guys have good ideas, and OSGI was one of those good ideas, so I took some inspiration from there. Yeah. Then we have technology that called remoting, and it's basically a framework that allows you to do inter-process communication. So have some class in one process, call a different class or methods of a different class in a different process. This also allows you to build things like SOAP and REST web services in C++, but it's also used in order to bridge the C++ word to the JavaScript word, as we'll see later. And finally, I've taken the V8 engine from Google, which is also used in the Chrome browser and in Node.js, and integrated it with everything. So this gives you the possibility to write some parts of your applications that, very quickly in JavaScript. So actually the whole thing here, there is nothing IoT specific in it. It's a pretty nice platform that you can use to build any kind of C++ application, from a client application to a server application. So to make the whole thing IoT specific, I've added some additional frameworks and classes. For example, we have C++ interfaces for different kinds of sensors, like temperature sensors, accelerometers, GPS receivers, and so on. So basically, all the usual sensors that you need in most IoT applications. You can, of course, also define your own sensor classes. Then we have support for different protocols like MQTT. The Core protocol is coming soon, which is kind of web services for smaller devices. It's basically a binary version of HTTP and JSON, optimized for very small devices and for sensor networks that provide limited bandwidth. Then we have a couple of services. For example, you can post Twitter messages or send SMS messages, things like that. And finally, we have a built-in web server that already provides a couple of built-in web applications that you can use to quickly get started, and you can also add your own web pages. The whole thing is open source on the Apache license this time. So back then for Boko, I used the Boost license. Now I've decided for the additional parts to use the Apache license because with the new project, I not only want to reach C++ guys, I want to reach the broader community, and the Apache license is just wider known in the whole developer ecosystem than the Boost license. Yeah, everything is built in C++, of course, for best performance and efficiency. Although JavaScript is used for some parts of the web interface, both, of course, on the client side of the web, but also on the server side of the web interface. It's all based on a quite major proven code base. Boko libraries have been used for more than 10 years now in all different kinds of applications. The Google V8 engine is very widely used, especially on the server side with the Node.js tools. Then we have Eclipse PAHO, which is a C implementation of the MQTT protocol, which we're wrapping in C++. We use SQLite so that you can put a small database directly on your device. We're using some well-known technologies from the JavaScript client-side browser-based development like Angular, jQuery, and so on. And yeah, as I said, there is a built-in semi-automatic C++ to JavaScript bridge, which I'm going to talk a bit later on. The whole thing runs on your typical Linux-based devices like Raspberry Pi, BeagleBone, Intel Edison, and so on. Also, of course, on custom devices. And another nice feature is you can prototype everything on your desktop Linux system or on your OS X system, and then easily move your code to the device. This is a quick overview of the different sensors that are already implemented and the web services that we can talk to. And of course, everything is not just done for playing around. The background is to build a solid platform that can be used to build professional devices, of course. And there are different kinds of features that make that possible. So, for example, a big topic is integration of mobile devices with embedded systems. And a good way to do this is put a REST API on your device and use the REST API from your mobile apps. This is something that you can do. You also have a kind of an apps concept on the device. So you or your partners and customers can write little apps in JavaScript that run on your device. You can build things like app stores around that, and in this way provide additional services. And also you can fully customize the web interface. So the web interface that you see here is just the default interface, but you can fully change it to whatever you need to. So to make things more interesting, I'm going to show you a quick demo before I'm going into the C++ details of integrating with JavaScript. So for the demo, I have everything running here on my Mac, and also I have a couple of devices with me. So for example, this is a sensor, combined sensor for temperature, humidity, and lightness that uses the Zigbee protocol to talk wirelessly to my Mac. And on my Mac here, I have a little thumb USB stick that acts as the endpoint of the Zigbee network. I also have some nothing here that's called Tinkerforge, and this is basically a set of modular hardware components that you can use to easily prototype some device without having to burn your fingers with the soldering iron. And Tinkerforge is basically an open hardware project, so they have designed about 100 different modules, and the central point of the module is the so-called master, which is a little device that has a USB built-in and a microcontroller, and it uses USB to talk to a PC or Mac or any other Linux-based device. And they basically have a standardized interface to different kinds of sensors. Again, temperature, humidity, motion sensor, also input devices like rotary dials, GPS receivers, and a couple more, more than 100 different modules at this time. And they also have a very nice API that can be used from 20 different programming languages. Also, of course, from C and C++, and we have wrapped this API also in Machine.io. So this is great for doing the first step with actual sensors on a desktop system. So the first thing when you start Machine.io on your device is the login screen of the web interface. You can log in there. And what you then see is a screen that's very familiar from your smartphone. So basically you have different kind of apps that are running on your device, which can be implemented in JavaScript or C++. So for example, we have a console viewer that allows you to see all the debug output of your application directly in a browser. So when you're doing some playing around with your device, you don't have to have a secure session open to your device to actually see the log output. You can see it directly in your browser. Then we have an overview where we see all the different devices that are connected to your system. So for example, here we see down below, this is actually the XP sensor. You can also see there is the current value that the sensor measures. And if I put my finger on the light sensor, you should see the illuminance value dropping down to 0 or almost 0. It takes a little time because the sensor only sends the data every couple of seconds in order to save battery. There's also the Tinkerforge sensors visible here. Again, we have here the Tinkerforge light sensor, GPS sensor, which of course doesn't have a GPS signal in here. The humidity sensor, and here, for example, the rotary encoder. So if I turn the dial, you should see the value change as well. Then you have the concept of bundles, as I said earlier. So basically, the whole Machina.io consists of about 40 different bundles, and each bundle provides certain features to the whole system. And this makes the whole system very modularized, extensible. So basically, in your own device, you just add the bundles that you actually need. And so this makes it very scalable from very small devices to even bigger devices. And you can, for example, click on one bundle, see some meta information about it, like the version numbers and the dependencies. So it's also dependency management built in. And you can also click on install and install a new bundle. And this can be done by taking a bundle from my desktop. And dragging it here, and then bundle gets uploaded to the device. You can start it. And if we go back to the start screen, you see there is a new icon for the new bundle that we uploaded. And if I go to that, there's actually a live visualization of this rotary encoder here. So as I turn this, you see also the needle on the dial move. And this is actually using a WebSocket connection in order to get the sensor data from here through here to the web browser in near real time. And another nice thing that we have is the so-called Playground, which is basically a JavaScript editor built into the browser. And you can use this to write some JavaScript code, then click on Run, and run that code directly on your device. So in this case, in this example, we have some code that can send SMS messages. And in order to do this, we're basically, the idea behind this demo is we are checking the light sensor, and if the light goes below a certain threshold, we're sending someone an SMS message. So down here is some code that defines a callback function when the value measured by the lighting sensor changes. And if the value goes below a certain threshold, we call the send SMS function, and this function basically calls a web service provided by Twilio to actually deliver the SMS message. So that was a quick overview. Any questions so far? Yep.
Do you planning to support also Bluetooth low energy devices?
Yes, at least on Linux we have some basic support for Bluetooth low energy devices built in. It's based on the Linux BlueStack. And one of the devices that already integrated is the Texas Instruments sensor tag. Maybe you've heard of it. So you can actually use it here as sensor tag already with Machina.io if you have a Bluetooth LE or Bluetooth 4.0 adapter that's supported by Linux Blues.
Okay, thank you.
Yeah.
May I see the Machina.io? May I see the Machina.io as a competitor for Node.js? Into, let's say, I'm imagining a solution where you are dealing with web services. Mm-hmm. You are using Machina to get the REST and JSON, and after that to pass to C++ module to make the hard intensive processing. Mm-hmm. Is it possible to, do you know solutions where Machina.io it is used in such scenario? web services and backend with high-intensive C++, but the connection between web services and C++ to be done by Machina.io.
So you're talking about the backend, not the device, but the backend?
No. For instance, for Node.js,
Yeah,
you can create a C++ add-in,
yeah.
and you can pass through from web to your C++ code.
Mm-hmm.
You can pass data, and you can process it and get it back on callbacks and so on.
Mm-hmm.
I'm thinking if Machina.io, it is good for, it was used once into such solution to make the connection between the web and C++ world. Here I'm trying to point, because I was thinking to that solution when I took in consider also Node.js.
Mm-hmm. You can use Machina.io also for this kind of things on the server side.
Okay.
I don't see Machina.io as a direct competitor to Node.js. Node.js is more on first thing focused on the server side of things,
Yes.
not so much on devices, although it's also being used on Raspberry Pi and similar devices.
That's what I asked you. If do you see as doable, reliable in this part or not?
I do, yeah. And basically the main difference between Node.js and Machina.io is the amount of C++. Basically, in Machina.io, the big idea is to implement all the backend stuff in C++ and only have JavaScript as a scripting layer for application level, business logic kind of stuff. And Node.js is more of as little as required in C++, but everything else
Exactly.
in
That's
JavaScript.
why I'm still hesitating in using into my project idea the Node.js, just because I see it limited. It's just an add-in. It's an extension. You can do there some limited things, but if you are thinking to complex backend, then they should be done in C++. Then I see it a bit trickier.
Mm-hmm.
Maybe this add-in should be just a layer for a module that should be high-intensity process.
So another big difference is basically Node.js is due to its JavaScript focus basically single-threaded and uses a lot of asynchronous I/O and event-based architecture, which makes it very hard to implement certain things that require some computing and stuff like that. And Machina.io is more multi-threading based, so you can have multiple threads running their own JavaScript scripts and so on.
Yes, well, they have some ways to extend to multi-threaded, but yes, indeed, just an additional thread. It's for usual stuff. It's too less. Thank you.
Okay. So let's take a look into what's basically on the inside of Machina.io. We've already seen this picture, so just a quick more information about the different things that are part of this picture. So, of course, there are the Poco libraries, which have started in 2004. In the meantime, Poco has become a pretty nice open source project. We moved to GitHub end of 2012. And since then, basically, the contributions have kind of exploded. And now I'm in a nice situation that Machina.io is basically driven by a community. So if you've worked with Poco, you probably also know Alex, who is in the United States and also talks at different conferences there about Poco and what it does with it. So he does a lot of the community work right now. And I do a bit of the more end decision making and no longer so much actual coding, although I do I'm still the one who is finally responsible for putting the releases out, which is kind of the not so fun work, making sure everything works when the time comes to release a new version. We have about 100, a bit more than 100 contributors now who have contributed different parts to Poco, from a few lines of code for a bug fix to complete libraries that are now part of Poco. Everything is under the Boost license, and you can find it on GitHub and on pocoproject.org. So the next thing is the Google V8 engine, which is also, thanks to mostly Node.js, quite a widely used C++ project. It's basically a C++ library that you can integrate into your own code base, reasonably easy integrate into your own code base. There are a few issues that we're going to talk about. It has great performance because what it does is it compiles JavaScript to native machine code for Intel and ARM and MIPS architectures. And it's also under the BSD license, which makes it very easy to use in any kind of project, open source and commercial. Then we have the remoting framework, which is basically, if you have done some work in Java or .NET, there are similar technologies, basically frameworks that allows you to call methods across process boundaries. And with remoting, you can do web services, you can do quick, very fast, efficient TCP-based communication, and we also use it for the C++ JavaScript wrapper. And then there is the open service platform, which I already talked about, and also showed you what it can do with uploading new bundles and this kind of things. So how can we combine C++ and JavaScript? It's actually quite an interesting task to do, because we have two very varying words coming together. On the one hand, for example, JavaScript is inherently single-threaded and uses garbage collection, while C++, especially when you're using Poco, is multi-threaded, especially when you're doing things like the web server. Then there's the question how you can provide C++ objects to your JavaScript code, which is kind of easy if you have a static C++ object that stays there over the entire lifetime of the JavaScript. It gets interesting if you allow your JavaScript to create JavaScript objects that are actually backed by C++ objects. It gets interesting mostly because you don't know in C++ when the JavaScript garbage collector decides to remove the JavaScript object. And when this happens, you also have to delete the C++ object. And V8 has some mechanism built in. You can register a callback function when the garbage collector hits your object. And then in that callback function, you can also destroy your C++ object. But there is some optimization in V8 if your script ends and there are still objects on the JavaScript heap, then the JavaScript heap as a whole gets just freed, basically. And you never get a callback telling you have to actually delete your corresponding C++ objects. So basically what you have to do is you have to manually track every C++ object that's created through JavaScript, and when the script ends, destroy the object. This is, again, in an architecture like Node.js, not an issue, because in Node.js, the JavaScript that Node.js runs for the entire lifetime of the Node.js process. So if your process terminates, you don't care about basically the destructures of your C++ objects being called. But it's very different in Machina.io, where a script can run for a limited amount of time. For example, you can have a script that runs when the web browser accesses a certain resource on your built-in web server. In this case, the script runs just for the couple of milliseconds it takes to build the result, and then it's done. And if you imagine having a couple of 100,000 calls to the web server, you have to be very careful about cleaning everything properly up. So as I said, things are quite easy. If you just access static objects from a JavaScript, you don't have to take care of cleaning things up, or at least you just clean your known objects up when the script is done. The things get interesting when you actually create objects in JavaScript that have C++ objects behind them. Next, I'm going to show you how you can actually make C++ objects available to JavaScript using the V8 engine. There is the concept in V8 of function and object templates, and these are basically C++ classes provided by V8 that you use in order to make a C++ object available to JavaScript. And in order to simplify working with that, we have created a wrapper class, a helper class called wrapper, that you can use to simplify the work with that. And basically what you do whenever you want to make a C++ class available in JavaScript, you create a subclass of the wrapper class for your specific C++ class. You have to implement a virtual function that's defined in the wrapper class that's called object template. And you also have, of course, to implement wrapper methods for every C++ method that you write. This is how the wrapper basically looks like. As you can see, we have a virtual function called object template, which you have to override in a subclass. And then we have functions like wrap native persistent, which is actually a template that do the work for you most of the time. So basically, what you have to do first is you need to call the wrap native function for a static object. That's quite easy. You just create your object template, which you create in your virtual function in a subclass, and then you call the new instance function from the returned V8 object template class when you're done with it. It's a bit more work if you have to deal with objects that are created at runtime. In this case, we pass the C++ object into the function, which we call the native object. And then we again create an object template using the virtual method. We call new instance, like in the first part. And then what we need to do is we need to create a V8 external object, which actually references our C++ object. So we put in the pointer to our C++ object in here, and then we return everything. What we also have to do is manage all our objects that we create. And for this, we're using the wrap native persistent template function, where we again pass in a pointer to our C++ native object. Then we create a new weak persistent wrapper instance, which is a template that I'll show you soon. We call the wrap native that I showed you earlier, and set a few things, and this way the C++ objects basically become part of JavaScript. And this is the weak persistent wrapper class that takes care of managing the lifetime of your C++ object. As you see here, we have a registry class that basically collects all the C++ objects that are created during JavaScript execution. And that takes care of all the properly releasing your C++ class objects. The way this all looks like is in your JavaScript, you have the JavaScript object. This JavaScript object has, via the V8 external class, basically a pointer to a C++ object that resides on the C++ heap. There is also the weak persistent wrapper instance, which basically takes care of the lifetime management, which also has a pointer to a C++ object. And there is also a reference from a JavaScript object to the weak persistent wrapper object. And what happens is when the garbage collector hits your JavaScript object, the V8 engine will give you a callback to your weak persistent wrapper object. And in this callback function, you can delete your JavaScript object. This is how it basically looks like for a simple C++ class. In the Boko libraries, we have a class called HTML form, which allows you to store the form parameters that you get from the web server when someone fills out a form or passes some parameters. And it basically has a couple of methods, but two methods are hash to check if a certain field is there or value is there, and get to get the actual value of the field as a string. And in JavaScript, we call it this way. If our form has a field called name, we extract the name of this field. For that Boko HTML form class, we need to provide a wrapper function that's called the HTML form wrapper, which is derived from our wrapper class. We have to override the object template function, and we have to provide a static method for every C++ method that we want to expose to JavaScript as JavaScript method. In this case, we have hash field and get field, and in the real implementation, there are a couple of more methods. And basically, what you do is in your object template method, a couple of lines of boilerplate code that I'm not going into the details. And basically what you do is once you have your JavaScript object, which is created here, or your object template, you set basically a JavaScript property for every method that you want to expose. In this case, we set a property for hash field and another one for get field. And then we simply return this object template to the V8 engine. And the other interesting thing is how to implement these wrapper functions like get field. When JavaScript code calls the getField method, basically this getField function gets called, which gets a V8 function callback info object that contains all the parameters basically and a couple of other things. We can see if we have the correct number of arguments. Then what we do is we extract the underlying C++ object, in this case the BokoNet HTML form, using the unwrap native function that's implemented in our wrapper class. Then we convert the JavaScript arguments to string, the name, and if an optional second argument is provided, we can use that as default value, and then we just call the C++ method of our HTML form object and return the result. Now this gets a bit boring if you have to do it for hundreds or more of C++ classes. So what I have done is I have taken basically the remoting framework that I've talked about and thought basically a call from JavaScript to C++ is very similar to a remote method call, because you have to do things like deserialization of the C++ parameters to something that's digestible by JavaScript and vice versa. And so we're basically using this. And what you do is you create a JavaScript class, in this case an interface for a sensor, a very simple interface that has an event or signal slot for value changes. So with value change, you can define a callback function either in C++ that gets called whenever the value changes. And you also have methods for getting the current sensor value. And then you run everything through a code generator, and you end up with a lot of source files. So basically this is the sensor class, and everything else is basically required for doing the nasty work of translating between JavaScript and C++. So basically in a traditional remote procedure call, you would have something like a proxy object on the client side that goes through transport, that does the actual network communication, to a listener in the other process, which then does, again, serialization and calls through a service skeleton through your actual service object. In JavaScript, basically this becomes the JavaScript wrapper object, which invokes via the existing remoting infrastructure your service object. And as a result, in JavaScript, you can obtain your sensor object. How this is done is shown quickly in a few seconds. And then you can define a JavaScript callback function for the value change event. And you can also invoke the functions of the sensor event object like ready or value, all without having to do manual implementation of these wrapper classes, basically. And now for the fun part, showing some JavaScript code that's usually used in your Machina.io based applications. So the first question is, how can I actually find this C++ object from a JavaScript code? And for this purpose, we're using OSB, and OSB has, beside the concept of bundles, also a concept of services and the service registry. And the idea is every bundle can register an arbitrary number of services, and services can have a name, and services can also have an arbitrary number of properties that you can use to find a service. And basically, all the services that are available in Machina.io are using this automatic wrapper mechanism, so they're also available in JavaScript code. So what we do here is we write a little JavaScript module that searches for different kinds of sensors and returns them inside a JavaScript object. So what we do is we go to the service registry, which is a global object available in your JavaScript, and call the find method, and we search for a service that has a property io.machina.physicalQuantity is illuminance. So this basically means gives me a light sensor, and I don't care whether this is a Zigbee light sensor or a Bluetooth light sensor or some other kind of light sensor. I just want some service that acts as a light sensor. And this will usually find 0 or more instances of the service, and then you can, in this case, we're just taking the first one that we find and getting the service instance and assigning it to our JavaScript object. We do the same for temperature and humidity. And there's also the possibility, if you know the specific name of a service, you can also use the find by name method to find a very specific instance. Another thing that you can do is you can access SQLite database through the Boko data library, which is exposed to JavaScript using the DB session object. So we create in our script a new DB session object, also get some configuration data from the application's configuration file, which actually uses the Boko util abstract configuration framework, which some of you may know. So this is also available to JavaScript. And then we write a simple data logger that basically periodically reads a value from the sensor and writes the sensor to a SQLite database. And for this, we can use the DB session object and execute some SQL statement from a JavaScript code. It basically works the same as the Boko data layer in the Boko libraries. We also have a set interval in JavaScript as part of Machina.io that allows you to implement periodic tasks. And in this case, we periodically get the current sensor value and write into the database. Here is another sample. Another thing that you can do is write so-called JavaScript servlets, which are basically JavaScript scripts that are executed when certain pages on a web server are called. And in this case, we're writing a little script that gets the data from the database, like here. Record set is db session execute. We execute a select statement on the database. Then pack everything into a JavaScript object, convert the JavaScript object to a JSON document, and send the JSON document to the browser. Okay. Here is the final sample of how to send data to a web service using MQTT. Again, MQTT client in Machina.io is a service, so we're using the service registry to find an MQTT client for a specific service, in this case Amazon. Then we create a payload in the form of a JSON document, and we send the payload to the server. Okay, let's skip the last sample. Any questions?
How do you execute the JavaScript? Do you create a new thread for every script?
Basically, yes.
Okay. And all function calls are synchronous, not like in Node.js where...
We have actually a mixture. There are some, you have seen there is this event mechanism where we can define callback functions. So this is basically a way you can have your JavaScript call non-blocking functions and get notified when the value is available via the callback. But the basic idea is that not everything has to be completely asynchronous because everything is running in its own thread, so it makes it a bit easier to write certain things.
Okay, thank you.
So what are the basic requirements to run Machina.io? Has it only been used on Linux platforms so far, or has it been ported to smaller platforms as well, running any sort of RTOS like ThreadX or whatever?
Right now it only works on Linux and macOS, and theoretically it can also work on Windows, but we haven't built the build infrastructure for that. So basically the code base is cross-platform, but the build system is not yet completely available for Windows. Boko has been ported to VxWorks, and it could also be ported to maybe ThreadX or something like that, but this hasn't been done so far. I guess the major issue here is with Boko the amount of flash storage that you have on your device, because Boko is using C++, the whole C++ infrastructure, and so we have a certain minimum size of the executable. So basically, if you use the Boko web server, the minimum that you get out on an ARM-based system is about 2 megabytes. Okay. And so it's not really suited for very small systems, but there is nothing that would prevent Boko from being ported to another RTOS. Just basically, the work needs to be done. And the system requirements should be, of course, there in regards to especially memory. It's not so much an issue of CPU performance. So we have actually run Boko-based applications on a Linux system that runs on an ARM7 with ARM9 with 75 megahertz, and it was 8 megabytes of RAM and 4 megabytes of flash.
Okay. Thank you.
Last question.
Okay.
If I understood this correctly, I saw it in the last slide. All communication between the client and the server is dumped to a string and sent as a string and re-evaluated on a server. Is that true? Because you had this JSON stringify there. So all the data is put into a string.
Yeah, of course.
And sent to the server.
It depends on the specific service that you're using. So the most cloud services that provide some IoT services actually use JSON as serialization format. And right now, a little restriction in Machina.io is that we cannot really deal good with binary data. But
Because
again,
I could imagine that on the sensors, maybe you need to rely on very precise floating point values, and that could be a bit of a problem, right? Because when you put a floating point value into a string and re-evaluate it again afterwards and put it back to a float on the server, it could lose precision and could not be... So has this ever been a problem? Or
for most sensors, actually, it's not a problem, because if you take typical temperature sensors, they're not very precise.
Okay, yeah, and that
so
example.
you don't need more than 2 fractional
Okay,
digits.
so precision issues are no
It could
issue
be, of
currently?
course, for certain things, it could be an issue, but then you always have the possibility of doing this kind of things in C++ and use the full floating point.
Okay, but you can transport the value between the client and the server also via non-string or via binary data?
If you have a protocol that supports binary, you can do that.
So this could be used
It
also
could be
in
used,
Machina.
yeah.
Okay, thanks.
Okay, if you still have any more questions, I'll be around for the afternoon, so you can grab me outside and